morning. So today I'm going to tell you a little bit more about cryptographic modeling math, and more specifically about one of the constructions and also some attacks that we came up with against this. So what I will be doing today is going to work with examples of question psychology, and basic analysis, and mathematics, charisma, so we already heard several talks that introduced cryptographic modeling and apps that we try to go to the goal that we want to achieve with this cryptographic tool. Our goal was to be able to compute and encode data. So we want to be able to compute on something like secrets or parts of the organization with multiple knowledge. So if we give this definition, one would immediately think about Polynomial encryption because they sound very similar to the definition of Polynomial encryption, but yet this is not exactly the same. And let's see what are the differences here. Well, the similarity between the two images is that in both cases we want to be able to encode and then once we have these encoded values, we want to be able to evaluate different polynomials on these encoded values, and the results that we want to get is an encoding of the polynomial evaluated at the initial solution. So this is the similarity between the two images. And now what is the difference? Well, in the case of an encryption scheme, we want to have the property that without the secret parameter or the secret key for the scheme, we are not going to learn anything about this information. And once we have the secret key, we can decrypt and we can learn just any of the information. In the case of multilinear math, we want to have a little bit different thing. We want to have a public value, a public parameter that allows us to learn some limited information about the encoding. And what is this limited information? It's basically whether the encoding value So the notion of cryptographic multilinear math was introduced by the in 2003, and their goal was to obtain a generalization of bilinear math. And they predicted that this utility could have harnessing consequences. I'm not sure whether they really realized what the consequences of this utility cryptography, but they definitely had good intuition. So the goal of this multilinear math was to expand the ability to compute or encode values beyond quadratic math. Because we have already used bilinear maths that allowed us to compute quadratic functions and encoded values, and now multilinear maths we're aiming to take this one step. So I just want to go and talk on one side about the applications of this multilinear math that are really far. So already bilinear maps were enabling us to construct many new cryptographic primitives that we didn't know how to do without them. Some examples are identity-based encryption, some limited forms of attribute-based encryption, data-based encryption, and also some efficient monitoring tools. I don't expect you to know what these primitives are, but I just trust you that these are functionalities that are of great interest for us, and you were only able to get this with multilinear. Now, what happens with multilinear math? When they introduced the nodes, and even though they didn't know how to construct them, they already gave a couple of examples that we can construct new primitives using this multilinear math. One of them was the one-round annual determinant system, which can construct new serializable, and they construct new signatures, they have also random constraints, of these constructions were shortly after attacked and broken to different extents. So the construction of Polynomial quantum security, the first attack of this construction was given by Hanley, and Stelle. Later, Bonnet, and Zimmerman kind of extended this attack, and also our work, which I will be familiar about during this presentation, kind of extended even further this attack on the work of quantum security. As a response to these attacks, there is a new kit by the same authors for the field, which so far does not acceptable. Also, the work of James Zimmerman and Point came about, which was trying to fix some of the attacks on PH13, which some of the attacks were kind of introduced even in the original work. They were not really complete attacks, but they were showing some weaknesses of the construction, and we had some extension of this attacks in our paper, and then also Hu and Gia gave even stronger attacks, Zeroizing attacks. And as of a few days ago, I saw a note online that kind of showed that maybe we fixed it up completely. But that's what the current state. As you see, it's a bit fragile state. Okay, but let's continue and delve down into the definition of what So, the original definition of multilinear map is saying that the multilinear map is defined over two groups, G1 and G2 of the same order, prime order P. And then a multilinear map is a map that takes in the first group and maps them into an output in the second group. And we want to have the following multilinearity condition, which says that multilinear maps on elements of the form that we want to take us to elements in the finite group, which can be represented as the multilinear map on the general and the end to the power of the product of all these forms in the initial. A further condition that we would like to have for this multilinear map is that it's not degenerate, which means that if we have include the multilinear map and generate the output, then we actually get a degenerate. So this is a general definition for multilinear map that is in the case when this n is equal to 2, we get the multi-number by this definition can also be extended to the arithmetic setting where the n group the resources So now multilinear map primitive can be defined with the following algorithms. So we will have an instant generation algorithm that basically produces the parameters for our multilinear map system. This would be all the groups, their generator, the size of the groups, as well as definition of the multilinear map system with the algorithm. Then we want to have an encode function that tells us how to take element x and produce an encoding of this element with respect to one of these sources. So I will and here we want to have the property that we have a unique encoding, which means that we basically could test for quality to encodings. So we also need to have a group operation that allows us to add encodings that group. And of course, at the end, we need to have the property for the And the first type of parameter assumption we want is saying that discrete log is hard. It means that an adversary is given an encoding of random element in one of the groups has only negligible probability to compute what is encoded. So this is the most basic parameter that we need. And for most cryptographic assumptions, actually we want another assumption to call and this if you have a memory and then you're given n plus 1 then this n plus 1 encoding together with an encoding of the target group that having the components the product of all of the elements is divisible from this random so this tells you that the multilinear algorithm allows us to compute and so if you one of the functions go up further, then you can also so this is a very useful and it's using most but so far I was talking about the using the real multilinear algorithm and in practice all of the that we have they actually don't what it is actually called the encoding. So let me try to define what are the differences between the ideal multilinear and what basic encoding is. So the first difference that comes with basic encoding is that what they define physical for multilinear requires that the encoding is now the basic encoding allow the encoding service so we will no longer have a unique encoding element, but actually all possible encoding and we will use this notion of sets to define what a state-weighted encoding system is. So this state-weighted encoding system will have a associated input where the values of the encoding will be, and also will have a system of sets, which are of the form that provides 8, where I will be the level of encoding, and A will be the element of the encoding. So what are the properties that we will require from this set? So the first requirement is that if we look at all the sets that describe encoding sets at some level I, they are disjoint. It means that each element A in R determines the set of its encoding at level I, which is disjoint. They don't have a encoding. It can be possible encoding. So now this is what an encoding at different levels of elements will be. Now we want to be able to actually apply this computation, different computation on the encoded value. And for this we want to define the different operations that we can apply to the encoded value. So first, addition, we would like the property for addition to be that if we have two encodings of two different elements, A1 and A2, that are at the same level, we describe to be at the same level I, then we have an operation addition that allows us to obtain an encoding of the value A1 plus A2 that is encoding at the same level I. And next, we want to have also multiplication that tells that if we take two elements, which this time can be encoded at different levels, I1 and I2, then we have a multiplication operation that tells us how to obtain an encoding of the product of the two elements A1 and A2, and this time this encoding will move to a different that the two will be high. Okay, so far I told you how to encode the something such that, for example, encoding, how we can do additional multiplication, so we can evaluate polynomials and other values. What we lost is that we now no longer have this unique encoding and we cannot test the quality. So what this will be substitute to this will be the zero testing. So zero testing will give us the ability to check if we have an encoding at some specific level, say, which will be our zero testing, which will be fixed together with the parameter in this case. It will give us the ability to check if we have an encoding at this level, zero testing level K, to check whether this encoding is actually encoded. So these are the properties of this K-weighted encoding system. So now, if we want to define again the algorithm that we need, so we have our instance generation algorithm that produces parameters that are the description of the K-weighted encoding system. So note that now we require that this parameter is flexible. So this instance generation with the second parameter, so if you remember what Dan was talking about, is that now this weighted encoding systems requires structured setting because this parameter is secret and we need to have a certain part of it. So apart from the secret parameters, we will have also the zero testing parameter, which will be found. And this zero testing parameter will allow us to test whether we have encoding from zero at some level. An encoding of an element A at level I will be basically something with a set of all possible encodings of this element at level I. We will have the addition and the multiplication operation that I already described, and the zero testing parameter, which zero. I just want to make a note that, in fact, the original definition of weighted encoding wanted to enable encoding using only public parameters, but this kind of extended definition that complicates the functionality, and for our attacks, and also if you make this extended definition, it kind of only helps with attacks. And since in this talk I will be presenting attacks, this is a much stronger section in terms of whether this is acceptable for attacks, so that's why we will focus only on the setting where encoding actually requires attacks. Okay, so now we have the definition of what a weighted encoding system will be, and now we are ready to move to the next code, which will be basically the attacks on the multilinear mapping construction that was proposed by the quantum computing department. So, what is the construction of CIP 13? So let's first see what are the system parameters, or this in generation, what is the So we have two sets of primes, P1 to Pn and then P1 to Pn, where the primes G sub I are much smaller than the primes. So we have this set of primes. So we call them big primes, small primes. Then we have a modular exponent, which is the product of all of the times P1 to Pn. We also have a level parameter, so this will be used for the encodings that are associated with a particular level. That this level parameter is using this at x0. Now, in terms of what needs to be secret, all of these parameters need to be secret, all the two sets of primes, and the level parameter b. The modulus x sub 0 would be actually perfect factor, and this will be needed in order to perform multiplication. I also want to note that in this construction, you could easily define different types of encodings where you will be using different v sub I level parameters. But for the purposes of this course, there will be multiple possible cases where we are using one. So, how do you encode in Zeroizing? So, we will be encoding n tuples that live in the product of the v sub u1 to v sub ux. So, this will be our message space, and our encoding will be using the Chinese theorem. And more specifically, if we want to encode a message that's m1 to mn at level j, the first step will be to sample random values r sub I, which are much smaller than the primes p sub I. And once we have these small r sub i's, we will compute the values p sub I, which are basically the message coordinate m sub I plus the r sub I multiple of the primes p sub I. Once we have computed these values, our encoding for the message m at level j will be the CRT of the p sub I that we computed here, divided by the level parameter b to the power j. This is how what will be associated with the encoding at level j. And this is all computed modulus x. This is our encoded modulus. And again, if you want, in the more general case, your level could be some product of different v sub i's. You don't have to stick on the line. So this is what an encoding in CRT looks like. Can we evaluate? Can we compute with the CRT encoding? Well, yes, we can look at addition, and these are the components, the CRT components. We could contribute different multiple p sub I. So we could add two encodings that are at the same level. We require them for and then we will see that we get an encoding of the sum of the message. Here, the noise or the random noise that we are using for the encoding has changed. It's the sum of the two initial randomness in the two encodings. Similarly, we can multiply. So now we no longer use the two encodings to reach the same level. We are just moving to a higher level for the resulting encoding. And again, in this time, the noise, the random noise for our encoding grows a little bit more. So we were just adding here. We see some more complex expression for the noise, and we have to be aware of this because we need to guarantee that we have a boundary noise growth. Because our zero testing and the multilinear maps can work correctly only as long as we don't have a wraparound on this investigation in this module. So we have to maintain the property that this product that we're computing remains smaller. And this is kind of a caveat in constructions, module construction is that you can do your computation. It's also limited by this noise growth, and you have to set up your parameters with respect to how many computation you want to do. Okay, so we have encoding. We can add and multiply them. So the next question is how do we do that? So let's see how we construct the zero testing parameter. So the first step is we compute basically are the product of all initial p's of I except the I. We can see them as x of 0 divided by the I. So we compute all I of them. Note that we can have each of our points before, and then we're looking at series of values p1 to pn are in values. So we have to compute the series of the product of each of I prime with each of I. Then the series in this case just as the sum of all the values that we're computing series and then modulo x of 0. And this holds because we can see that each small piece of I divides all of the values here except 1. So, and this property will be using in the zero. So now we have computed this piece of I primes. What will be our zero test parameters? Well, we sample from I to n, we sample values h of I, again, which are random, but they need to be much smaller than the times piece of I. Now, our zero test will be computed as the CRT of the values where we multiply each piece of I prime, which is defined here, together with the corresponding h, and with the inverse of the corresponding piece of I. These inverses are computed modulo piece of I. So we take the CRT of the values of this form, and then we also multiply the resulting value with g to the power k, where k will be our zero testing value. And this is all computed modulo x of 0. So again, I can give you one moment to look at this. So this is kind of tying our zero test parameter to the level which we'll be testing. And these components here will basically be allowing us to cancel out the GI values only if from the encoding we are getting values that are modulo this amount. So let's see how we actually zero test once we have this case the zero test level. How we actually zero test if we have a zero test parameter in this form and an encoding at the zero test level. So again, an encoding at the zero test level will be a CRT of the values that are the noisy encodings of the components of the message and survive. So they are again of the form n plus some random corresponding quantity. And then we have all of these divided by g to the power k. And on the other side, we have the zero test parameters. So now what will be our zero testing check? We will be multiplying our encoding with the zero test parameter, and then we will check that the absolute value of the result is whether the absolute value of the result is small. So notice what happens when we multiply the zero test parameter and the encoding. Now we have a CRT of this of the product of the corresponding components. So it's of this form. Now we are using the property that if we have a CRT of values that are multiple of these pi primes, we can just compute this as the sum of these values mod x0. So now this is what a times piece of GT gives us. What happens if n is encoding 0, right? Our goal here is to check whether n is encoding 0. Well, if n is encoding 0, then these components disappear. And then we are left out only with the sum of this form. So we have a sum that depends on the p, I prime values, and then on the hi and ri's. the way we have chosen HI and RI was such that their product is much, much smaller than PI, and PI is the missing prime in this PI prime. So what this tells us is that this equality holds not only modulo x of 0, but it also holds over the integral, because we are guaranteed that we will know we won't have a wraparound on x0 in the case when we have an encoding of 0. So here we are guaranteed that if A encodes 0, then we can test that this product has a small value. On the other hand, if A doesn't encode 0, then this term here doesn't disappear. It's a large term, so the total value of this expression with high probability will be close to the size of the our modulus x0. And the same thing will happen if we are trying to zero test an encoding that's not at the appropriate level. So if we're trying to test an encoding that has any different level except k, then this z to the power of k will not cancel out the component coming from the encoding. And again, the result will be something large. So with this zero test thing component, we have the property that this value is small only if we are testing an encoding at the zero testing level k, and this encoding is an encoding of 0. Okay, so this is basically the description of the multilinear map scheme of CLT13. Now let's see how we attack this CLT13. Well, let's just give you a little bit of the chronology of the events that happened. So when CLT13 was published, it seemed to be even immune to the weak discrete log attacks that were a concern for the GGH13 scheme. So this CLT13 scheme seemed to be even better in that aspect. But this was only until the attack of Xion et al. That they gave the first attack on CLT13. Their techniques were based on this zeroizing type of attacks that rely on low-level encodings of 0. And this was a complete break of the scheme. Basically, with this attack, which we will see over the next slides, you could recover the private parameters for the encoding scheme, and that was it. So immediately after this attack was appeared on E3, so this is the year of publication, and actually it was only 10 months earlier. That's why these proposed fixes are with earlier dates. So Bonnet, Wu, and Zimmerman, and then Gark, Gentry, Halevi, and Zandri proposed some fixes, attempted fixes for the scheme that were aiming to avoid the attacks of Xian et al. However, in our work, we first extended the attacks on CLT13. We showed that we don't really need low-level encodings of zeros, and we can still mount the attacks that were proposed by Xion et al. This was also observed in the work of Bonnet, Wu, and Zimmerman. But we also showed that we could also extend the attacks to break both proposed fixes in these two works. And we also showed that these attacks could be generalized to break some simplified versions of obfuscation constructions. So here, simplified is very important because they don't correspond to any of the real constructions of obfuscation, and any of the actual constructions are not susceptible to our attacks. But if we simplify, then we can actually mount attacks. Okay, so let's jump into the description of the attack of Xion et al. So just to remind you, we will have a CLT encoding that each encoding looks to be of this form, where n is the number of primes pi that we are using, k is the zero testing level. For the attack, we will need several ingredients, which are three sets of encodings. And these three sets of encodings are of the following form. So we have a set A, which contains n encodings of 0. So if we have an encoding of 0, these all n's are 0, so that's why the encoding of this form, we have multiples of all the primes g. Then we have another set that contains n encodings. These encodings now are not, we don't impose any restriction on those. They can be encoding random elements. And then we have a third set, which contains two elements, two encodings. Again, we don't have any restriction on what type of elements they need to encode. And these two encodings will be the target of our attack. That's what we will be trying to distinguish between these two different encodings. So the requirement on these three sets is the following. We want to say that if we take three encodings, any triple of encodings from these three sets, we obtain an encoding of 0 at the 0 test level. Okay, so this is at the 0 test level, but it also needs to be an encoding of 0, which is true because our encodings in the set A are all 0. So if we multiply any A with something from B and something from C, we get an encoding of 0, and it's at the 0 test level. So we can apply the 0 test parameter. So this is the most general description of the type of sets that we need. In order to look at how the attack works, let's look at some simplified version of this attack set. Let's assume that we have only 2 primes and our 0 test level is 3. So now we will have 2 encodings in the set A and 2 encodings in the set C, and also 2 encodings in the set B. They all will be at level 1, and our 0 test level will be 3. So I was imposing all these restrictions that we have the product of any triple across these 3 sets to be at the 0 test level, and this was with a purpose, because this is how the attack will work. We will compute all products of 3 encodings from the 3 sets. So one of them, for example, will be of this form. We have here the components. They're all divisible by G1, and this needs to be G2. So we'll have a CRT of values of this form, and then we will have Z to the minus 3. So now we will apply the 0 test component to the product of A1, B, and C1. And what we will get is the following. So we will cancel all the G values. This was G2. And using the fact that this equality holds over the integers, because we have an encoding of 0, and both of these values are very small with respect to the modulus xi, we will have a sum of these 2 values after we apply the 0 test component. So these parts, which are independent of the values that we're encoding, we will give them names, alpha 1 and alpha 2. So they don't depend on the encodings in our attack sets. And now that we have computed this W value as the product of the 0 test, we make the following observation. We can actually write this value as the product of 2 vectors and a matrix, where the first vector has components that are coming only from the CLT encoding A1. So these are the CRT components of the encoding of A1. The last vector has components that are coming only from the encoding in the CLT encoding C1. So this is the second vector. And then the matrix that's in the middle has values that are only depending on the encoding in B. So you can easily check that if you multiply this vector with this matrix and then with the next vector, we exactly obtain this this sum. So this, like, I want to again emphasize that we don't know any of these values. The only thing that we have is W11, but we can imagine that it can be written in this form. It will have this representation. So now we can do the same thing. We can apply the same zero test check on using all the rest of the sets A and C, and the same encoding from the set B. So we will compute all possible triples with the same B and changing the two encodings in the set A and in the set C. Now, if we use the same representation for the values W that we had from before, we can again decompose this matrix W as a product of three matrices. Each of these three matrices depends only on the components in the encoding from the set A, from the set B, and from the set C. So now we have obtained a matrix. We have only this matrix, but we know that this matrix could be decomposed as the product of these three matrices. These three matrices, each of them dependent only on one of the encodings. So we have this already. We put it aside, and we will do. We can give the names in this form, the matrices that depend only on the encodings in A and C, and then we will do the same kind of computation, this time using the other encoding in the set B. So now again we will be computing triple of products of encodings from A, C, and the other value in B. We will be zero testing them, and in the exactly same way we will be obtaining another matrix which we call W prime, and which will be decomposed in exactly the same way. It will depend on the encodings in A, on the encodings in C, and then the middle matrix this time will be dependent on the other encoding in B. So it will be using the CRT components of the CRT encoding B prime. So basically what we have done is we have applied exactly the same step using the first encoding in B and using the second encoding in B, and we have ended up with these two matrices that have the same form, except that the middle matrix depends on two different encodings in B. Now, what we can do is we will look at the inverse over the rationals of the second matrix W prime. It will have this form, and now we can see that yes, you're right. Yeah. That should be V1 prime and V2 prime. So, and what's the next step is we have here this C inverse and we have here C. So why don't we just multiply the two matrices, and what we will get will be something of the form A and then A inverse, and then we will have a So what did we achieve? Well, what we achieved is that we obtained a matrix that has eigenvalues that depend only on the CRT component from the encodings in the set B. So now what we can do is we can recover this eigenvalue. And once we have recovered these eigenvalues, we can use them in order to factor our modulus x sub 0. Because these are the CRT components in the encoding of the CRT encodings in the set B, and they are all computed with respect to the primes p sub I, which are the factorization, give us the factorization of x sub 0. So this more or less completes the attack that was proposed by Sean et al. It shows us that we can really leverage the fact that we can obtain many zeros, which we can zero test. That's why it's called a zeroizing attack. Since we obtain many zeros, we are able to construct these matrices that basically allow us to decompose the components that are coming from the three sets. And then once we reach to something of the form that has eigenvalues that are only from the encoding from the set B, we can finish the attack. Is this clear? Do you have any questions? That's kind of so you will actually use also the original values in B, in the encodings of B, and then it's not immediate. We will look at values of the form B1 times the component B from the encoding B prime minus B2 prime times the value B1 from the original encoding, that's mod X, and then you will be getting something that's with high probability 0 modulo P sub I, but different from 0 modulo X0. And then you will be looking at the GCD of this value. So you will be using these two values together with the value of your original encodings in P to get a value that's 0 modulo P sub I and non-zero modulo X sub 0. And you will be looking at the GCD of this. Okay, well, I'm very ahead in my time, but let's see how much more I can tell you. So now I told you that the first extension of this attack that we had was actually removing the need of low level 0 encodings. So let's remind ourselves what are the three sets that we have. So in the original attack of Sean et al., they require that the values encoded in the set A are encodings of 0. We observe that we can execute the same attack even if these are not encodings of 0, as long as we maintain the property that any product of matrix A, B, and C is an encoding of 0 at the 0 test level. So now if we have a encoding, if we maintain the property that all of these triples are encodings of 0, we have the property that G1 will be dividing these values, which are the components with respect to the different primes, and G2 will be dividing also the product of the second component in the encodings. So now we basically maintain the same structure as before, but here we are keeping G1 as denominator and here G2 as denominator, because the only thing we know is that A11 times B1 times C11 will be divisible by G1, but we don't know which of them will be divisible by G1, but we can keep G1 in the denominator. So we can write the two matrices that we were computing before in a similar form, and then we can perform the same tricks as before. We can compute the inverse over the rationals of the second matrix, which will allow us to cancel the C matrices, and the D values will also cancel when we multiply W prime with W prime inverse. And we are again in a setting where we have a matrix that has eigenvalues, which are the ratios of the CRT components in the two encodings in the attack set. So we can proceed exactly in the same way as before. So not much. So this leveraging this attack to having no, to requiring no low-level zeros was not much harder than the original attack. So the next extension that we had was actually looking at the setting where we don't really have only a single monomial describing our the result of our zero testing. So let's look what was motivating this attack. This attack was motivated by the extension of Bonnet, Wu, and Zimmerman, which was called the immunization of COT13. So they tried to fix the problems with COT13, and let's see how they tried to fix the problems. They extended the way you are encoding. So they defined a new multilinear map encoding scheme where if you want to encode message M1, M2, so I'm just looking at the example that we have the reduced dimension to 2. If you want to encode such a message, you will be encoding it in the following way. You will sample these random values, and you will output 2 encodings that are CLT13 encoding. So you will be encoding 2 new vectors, which are constructed from the values in the original message, together with these random values that you are sampling. So basically, we construct the vector that contains the original message, and then 2 of these random values at the last 2 positions. And we'll encode this using CLT13. And then we have a second value, which is encoding this time all of the random values. And the important part is that this second to last component encodes in both A and A prime the same value. So now we can also observe that we can add and multiply these encodings. How do we add and multiply these encodings? Well, we just add and multiply component-wise. So each encoding now is a pair of original CLT encodings. And we can just add and multiply the corresponding coordinates. So we preserve the computation properties for this multilinear map. And now what is the zero test parameter? So we will have a zero test parameter for COT13. And then additionally, we'll also release 2 zero test encodings, which are CLT13 encodings. Here, we will have an encoding of the vector 1110, and the other one will be an encoding of vector 0010. Why do we have encodings exactly of these 2 vectors? Well, it will become clear when we see how we'll zero test. So the zero test will first multiply this T sub L with the first encoding A. So what this will do is it will cancel out basically the last random component. Then we will also multiply the second zero test parameter T sub R with our second component in the encoding. This will cancel all the random components except alpha. And then we will subtract the results. So subtracting the results, we have canceled all the betas here. When we subtract, we will subtract and cancel the randomness component in this position. And we will end up with an encoding that has in the first 2 components M1 and M2, and then the last 2 components will be 0. So now we can zero test using the original CLT zero test, and we will, yeah. What is the point of the fourth? I guess just adding more randomness. I don't have a very good answer. Why is it? Why it's the fourth? I think they just needed one more random coordinate. But I don't know. I don't know whether you have a better attack when you remove this last one. Yeah, that's a good question. Yeah, maybe we can look at it more carefully after that. Okay, so what what happened here? I mean, I'm omitting details. I have to tell you at what levels we're encoding all of these value, all of these vectors here and here, but they have a way that they make all of the levels work out, and it's not very relevant for our attack. So what is the bottom line here is that the when you're at the point when you're applying the zero test component in CLT, you no longer have just products of three CLT encodings, but rather you have these two products that are subtracted, and you are able to zero test only values of this form. So now what we say we have multiple monomials in an expression that we will be able to zero test. So how are we going to construct our attack sets? Well, our attack sets now will be this type of matrices that will be basically using the components of the new BWZ encodings. So the two components of the BWZ encodings are two CLT13 encodings. We will use them to form our attack sets, our matrices, and we will again have three sets of encoding such that we have the property that any product of three of them is an encoding of 0. So now we can do exactly the same as before. We will zero test each of these products. Now zero test is a little bit more complicated. We have to use also these t values. But the bottom line is that we can write the resulting values in exactly the same way, with the only difference that we increase the dimension by 2, because now we have all the components. So now the zero test in the first coordinate will be this minus this, and then we will multiply with the corresponding components from the A encoding and the corresponding components from the C encoding. So these multiple monomials, we basically designated different rows in our matrices for the different components that were for the different monomials that were coming from our zero test parameter. So we can easily extend this to any number of monomials. This would just require us to have more encodings in our attack sets. Before, we were able to launch this attack with only 2 encodings in the A set and 2 encodings in the C sets. Now we will need 4 of them because we increased the dimension of our matrix twice. And then from there on, we are kind of doing exactly the same. We are using the other triples with the other elements in the set B, and we can compute the inverse, and we are again in this setting where we have a matrix with eigenvalues that depend only on the CRT components of the encodings in B. Okay, so I'm already out of my time. I can tell you another extension of the attack, or I can wrap up here. Okay, sure. So the next extension of this attack was trying to break another proposed fix for CLT13. So this was the fix that was proposed by Garg, Gentry, Halevi, and Zander. So how are they proposing to change the multilinear map encoding? So now if the new encoding algorithm was the following. If we want to encode a value m, we will embed the encoding of this value m in a larger matrix that consists of different encodings. And then we will multiply, I will tell you what these encodings are. And then we will multiply on both sides with a random secret matrix T, some dimension D, D times D, which you choose as part of your parameters. And then on the other side, you will multiply with the inverse of this matrix. So now what is in the middle? In the middle, each of these means encoding of a random value. and then each of this means encoding of 0. So we have in the lower right corner an encoding of our original message. This is the CLT encoding of M. And then on the diagonal, we have encodings of random elements, and everywhere else in the matrix, we have encodings of 0. So this is how the new encoding would be working. Again, the goal is to avoid having at the end just a plain CLT 0 test. Now the 0 test will be extended in the following way. You will compute these 2 additional vectors of encodings, which are computed in the following way. So the first one will be multiplied on the right by T inverse. This is because we will need to cancel out this matrices T when we 0 test. And then it will have the last component in this vector will be an encoding of a random element, and then the rest of the elements will be split. The first half will be encodings of random elements, and the second half will be encodings of 0. The other vector will have embedded the CLT 0 test parameter, the matrix T, and then it will have split the values in encodings of 0 and encodings of random elements in exactly the opposite order. So all of these encodings here will be at 0 level for the CLT. So basically what will be happening here is that the encodings of 0 will be canceling out all the random encodings in this matrix that was used in the extended encoding. So let's look again at what we have here. So we'll have 2 vectors that one will multiply on the left. It will cancel out the matrix T, and it will cancel out the first half of the random elements on the first half of the diagonal. And then what we multiply on the right will cancel out T inverse. We'll cancel out the random element in the second half of the diagonal. And at the end, we will also have the CLT 0 test component. So now a 0 testing will be multiplying the encoding with these 2 vectors, and the result will have this form. It will be an encoding of the message multiplied with something random that's coming from the last component here, and then plus an encoding of 0. And this expression now will be the expression that will be 0 tested with the original CLT encoding. So you can see that this one will still have the property that it's small when we apply the CLT 0 test, if and only if the message M was actually encoding 0, which will cancel this additional randomness. So now this seems kind of different. Well, let's see if we prepare again our attack sets. These attack sets will be now just the new type of encodings, this extended GGHZ encodings. So we'll have as many of them as the number of primes in the original CLT scheme and the dimension that we chose for these extended matrices that come from the GGHZ encoding. And now we can just do the same thing. We will be computing products of triples, and we will be 0 testing them. Now we can designate all this left part to be this vector, to call it a vector A sub I. This whole left part, again, is dependent only on the encodings in the set A. And this right part, again, is dependent only on the encodings of the set C. So what we'll obtain in this time is that if we apply all of our tricks, we compute the matrix W, and then we compute the matrix W prime inverse. When we multiply them, this time we will have something more complicated. This will be a block diagonal matrix. where the blocks on the diagonal will be of the form of the encodings that are coming. This B0 and B1 will be the components coming from the encodings in the set B. So we will have these whole matrices, one of them mod P1 and the other inverse again mod P1. And we'll have the same for the rest of the diagonal using the different primes. So now we cannot directly compute eigenvalues because we no longer have guarantee that these eigenvalues are rational. So instead of this, what we will do is we will look at the characteristic polynomial of this matrix, and we will observe that this will be a product of the characteristic polynomials of these block matrices that we're obtaining on the diagonal. So our approach here will be to factor the characteristic polynomial of this matrix that we were obtaining. And once we have factored this characteristic polynomial, we will use this to evaluate the factored polynomials at these block matrices. And then using Katie Hamilton, we will continue to recover the primes pi, where we will be relying on the fact that these factors of the characteristic polynomial, when we evaluate them on these block matrices, they will give us something that's equal to 0 mod pi, but with high probability will be something different from 0 mod x0. So now we could use again the GCD to get the factors p sub I. So the attack here on this extended scheme required a little bit more extension on our original steps. But so now I think I'm already 10 minutes over. I have one more attack, which I don't know whether it will be of interest. This will be an attack on the simplified obfuscation scheme. It will take more time of actually describing what the obfuscation scheme is than the attack. So if you're interested to know more about the obfuscation, you should say you want to hear about it. If you are interested only about the attacks, then I can just wrap around. Okay, then I take this as no. Like silence means no.